Welcome to FMSP Online Revision. This session is for OCR FP2 and the topic is integration. So we'll start by having a look at the specifications for integration and then we'll work through a few questions. So the specifications, first of all, we need to be able to integrate 1 over the square root of a squared minus x squared, 1 over a squared plus x squared, 1 over the square root of x squared minus a squared, and 1 over the square root of x squared plus a squared. Now it's worth mentioning at this point that you do have formula books that will help you with this. So the square root of 1 over the square root of a squared minus x squared you should recognise and look up and see that it's got something to do with inverse sine. 1 over a squared plus x squared, again, should be familiar, and that's the inverse tan. 1 over the square root of x squared minus a squared is going to be inverse cosh, so your hyperbolic function's coming in there. And similarly for this one, it's the inverse of sine. But do make use and use your formula books to help you here. So we've got to use appropriate trig or hyperbolic substitutions for evaluation of definite or indefinite integrals, and also it mentions that t equals tan a half x is included. So you do need plenty of practice at integration, but that's what we need to be able to do. In part F, derive and use the reduction formula for the evaluation of definite integrals in simple cases. And then in part G, understand how the area under a curve may be approximated by areas of rectangles and use rectangles to estimate or set bounds for the area under a curve or derive inequalities concerning sums. So we're going to have a look at each of these sort of sections. The first one is the tan t equals tan a half x substitution. So we'll use this as a reminder of how to do a substitution. A couple of things that are useful. This sin x equals 2t over 1 plus t squared and cos x is equal to 1 minus t squared over 1 plus t squared. Just remember these actually have come from your formula books. So I've put them in a box there, but do remember that. You can look them up. And then this is the technique that we will need if we're going to use the tan x over 2 substitution. So t equals tan x over 2. So differentiate to get dt by dx, a half sec squared x over 2. But of course we know that sec squared is equal to 1 plus tan squared, so it's 1 plus t squared here. But when we're doing a substitution we need to replace dx because we'll need to be integrating with respect to t. So I've just rearranged this to find dx is equal to 2 over 1 plus t squared dt. So that is the information that we need to start with. So let's just see now how we're going to actually do this. So we've got the integral of 1 over 1 plus sin x plus cos x integrated with respect to x, and now we're going to make the substitution, and so I'll put in 1 is alright. Sin x is going to be 2t over 1 plus t squared, and cos x is going to be 1 minus t squared over 1 plus t squared. And then we'll substitute in for dx, which is 2 over 1 plus t squared. And now we're integrating with respect to t. Now at this stage, you know, the whole point of making a substitution is that your integral should become easier. So just see that in the denominator here we could take a common denominator of 1 plus t squared, which will then, if we are dividing, would come up into the numerator and cancel out with 1 plus t squared. So in fact it does become a lot simpler. If we've taken a common denominator, then that would be 1 plus t squared. And then we'll have the 2t from the middle term, and we'll have the 1 minus t squared from the last term, and we've divided through by 1 plus t squared, so we're now left with that. And hopefully you'll see that that t squared and t squared cancels out, and so we end up with the integral of 1 over 2 plus 2t times 2 dt. In other words, the integral of 1 over 1 plus t. And that, of course, you should recognise hopefully as a log integral. So it's going to be the log of 1 plus t plus a constant, because it's an indefinite integral, but we need to substitute back in, and what I'm going to do is just take my constant as k and include it with the logarithm. So all I'm going to do now is to substitute back in t is equal to tan x over 2 and we have our answer. So it's an integration by substitution. As I say, all of this you could work through at the beginning so that you know exactly what you're going to be substituting in, and then it's just a matter of working through it carefully and trying to simplify it as much as possible. In terms of marks, there were 5 marks for the question. So you got a method mark here for substituting all this in, but you also got a mark for working out dx. So in a sense, by the time you got to this stage, you will have had 2 marks. You then get an accuracy mark for simplifying it, and then a method mark for integrating to get log of 1 plus t and a constant, and then substituting another accuracy mark just for substituting back in correctly. So the second question we're going to look at now involves the reduction formula. So that was the second sort of section in our specifications. So we'll have a look at that. So it is given that for n greater than or equal to 0, I of n is equal to the integral between 0 and a half of 1 minus 2x to the power of n times e to the x dx. First of all, we've got to prove for n greater than or equal to 1 that I of n is equal to 2n I to the n minus 1 minus 1. And having done that, we've got to find the exact value of I3. So reduction formula will frequently turn up in these exams, and more often than not will involve integration by parts. This one involves integration by parts, but the other technique can involve trig or hyperbolic functions. So just be aware of that. It's not always integration by parts. But that is certainly what we're going to need to do here. So if we let u equal to 1 minus 2x to the power of n, and that means then dv by dx will be equal to e to the x. We just do that up here. And then we will need du by dx, which will be minus 2n 1 minus 2x to the power of n minus 1. So I'm just writing that up there so we have enough room to write this all out. So I of n is equal to a half of, between 0 and a half, 1 minus 2x to the power of n e to the x dx. So that's just writing down the question. Now I'm going to use our integration by parts. So remember, integration by parts says that the integral will be equal to uv, so that will be, and between the limits 0 and a half, so that will be e to the x upon 1 minus 2x to the power of n between 0 and a half, minus the integral of v du by dx. So v du by dx, so there's a minus sign there, which if I combine it with that minus sign will give us a plus. So we'll have 2n upon 1 minus 2x to the power of n minus 1 times v, which is e to the x. And we've got to integrate that with respect to x, and again the limit's 0 to a half. So just be careful that you get that first stage of integration by parts correct. So uv minus the integral of v du by dx. So we can work this first bit out. So if x is equal to a half, then that term is going to be 0, so we would get 0. And then if x is equal to 0, we'll get e to the 0 times 1, which is just 1. Now, if we actually do this, I'll take the 2n out, because that's just a constant, and what we're left with is 1 minus 2x to the power of n minus 1 e to the x. And again, between 0 and a half, and hopefully you can see now that what we've got is we've got a minus 1 here, and then we have 2n lots of the integral, but this time the integral is to the power of n minus 1, so it will be I to the n minus 1. So we have now established the result that I of n is equal to 2n in minus 1 minus 1 as required. So 4 marks for the question. So you got a method and an accuracy mark here. So a method mark for attempting integration by parts and an accuracy mark for getting it correct. You got a method mark for using the limits correctly and an accuracy mark for establishing this result correctly. So that was part 1, and then in part 2 it says find the exact value of I of 3. So I've just written down the results that we had from question 1 here. So what we're going to do then, we want to find I of 3. So I of 3, so we're using this result, will be 2 times 3, I n minus 1, so that will be I2 minus 1. So 6i2 minus 1. And then we need to work out I of 2, so that will be 2n, which will be 4. I of 1 minus 1. And I of 1 will be 2i of 0 minus 1. Now, this stage, of course, we should be able to work I of 0 out. So I of 0 will be the integral between 0 and a half of, if I of 0, then n is equal to 0, so this expression will just turn out to be 1, so it is literally the integral of e to the x. And if you evaluate that, then when x is a half, you'll get e to the half, and when x is 0, you'll get e to the 0, which is 1. Remembering, of course, that the integral of e to the x is just e to the x. And then we can substitute those numbers back in and work backwards, so that means e to the 1 will be 2e to the half minus 3, and then continuing to work backwards, I of 2 will be 4 lots of that, So 8e to the half minus 12, take away another 1, so 8e to the half minus 13, and then I of 3, which is what we want to find, 6i of 2, so 48 e to the half, minus 6 lots of 13, which is 78, take away another 1, is 79. So we now have the exact value of I3. There were 4 marks for doing that, so you get 1 mark for getting one of these written down correctly. You got a mark for working out I of 0 to be e to the half minus 1, and then you got a method mark for substituting back, and an accuracy mark for getting the answer at the end. So the last question now we're going to look at involves the last section on integration about areas and using rectangles to approximate areas. So this question, it says the diagram shows the curve y equals the cube root of x together with a set of n rectangles of unit width. By considering the areas of these rectangles, explain why the sum of cube root of 1 plus cube root of 2, etc., right up to the cube root of n is greater than the integral of cube root of x between 0 and n. Then in part 2, by drawing another set of rectangles and considering their areas, show that that expression, the sum of the rectangles, will be less than the area if we integrate between 1 and n plus 1. And then in part 3, hence find an approximation to the cube root of n from 1 to 100, the sum from 1 to 100, giving your answer correct to 2 significant figures. So let's have a start by looking at the first part. So in this particular case, it's just 2 marks here, so we just need to be careful how we write this down. But the important thing to see is that the area of the rectangles between 0 and n is definitely bigger than the area. They lie above the curve. So what we want to write here really is something to the effect that the sum of the rectangles from 1 to n is greater than the area under the curve. From 0 to n. And we just need to make sure that we justify that answer, so that means that the cube root of 1 plus the cube root of 2 plus right up to the cube root of n is greater than the integral of the cube root of x with respect to x between 0 and n. And basically there was going to be 1 mark for explaining carefully that this area was greater than that. 1 mark. So 1 mark sort of for each bit. So just be careful that you explain that in terms of lying above. And then in part 2, it says by drawing another set of rectangles and considering their areas, show that the same sum is less than the integral of cube root of x between 1 and n plus 1. And the trick here is to shift the rectangles 1 unit to the right. So if you look at the diagram I've done here, what I've done is I've moved the rectangles 1 unit to the right. So this time we're considering the rectangles which are starting at the left hand coordinate. So each of these rectangles are underneath the curve. So by doing that then, so by shifting rectangles, and you need to explain that you're doing this 1 unit to the right of the area, then that means rectangles, then the sum of the rectangles is less than the area under the curve. And again, we just want to try and explain that as best as possible in terms of words. So that means that when we take this sum for the cube root of n, if we go from n equals 1 to n, so we're summing all of these rectangles, then that will be less than the integral between 1 and n plus 1 of the cube root of x dx. So you must have the correct limits, so you must show these numbers correctly on our graph. So you're getting B, 1 mark for the sum of the rectangles, you're getting 1 mark for having the correct limits, and you are getting 1 mark for showing this clearly on a diagram. So the diagram is important. And this limit, of course, is also very important because, of course, it ties in with the fact that we've shifted the rectangles 1 unit to the right. So having that information, we now are being asked to find an approximation for the sum of cube root of n between 1 and 100, giving our answer to 2 significant figures. So what we know is if we go from 0 to 100 of the cube root of x, if we integrate, if we find that integral, then we know from what we did in part 1 that the sum of the cube root of n from 1 to 100 is going to be greater than that integral, but at the same time it's going to be less than the integral if we go from 1 to 101. So that's the result then from part 2. But of course we know that this now, the cube root of x dx, we know we could integrate that and we would get, so you integrate the cube root of x, x to the power of a third, you'll get x to the power of 4 over 3 divided by 4 over 3, so 3/4 of x to the power of 4 over 3. And if we evaluate that between 0 and 100, then we get 3/4 of 100 to the power of 4 over 3, which is approximately 348. Now we're asked to give our answer to 2 significant figures, so I've rounded that to 3. And then I'm going to do a similar sort of thing, but this time I'm going to integrate from 1 to 101. So the same integral, but this time we're evaluating it between 1 and 101. So that will be 3/4 times 101 to the power of 4 over 3 minus 3/4 times 1 to the power of 4 over 3, which of course is just 1. And that, if you work it out, is approximately equal to 352. Now we're asked to give our answer to two significant figures, so each of these is going to be 350 to two significant figures. So the approximate answer value is 350 to two significant figures. So 3 marks for that, and really it was just a matter of seeing this is the result that you got using parts 1 and 2, that the sum was between these two integrals. But you basically got a method mark for that. You got just 1 accuracy mark for this, working out the values, and then an accuracy mark for giving the value to be 350. So I'm going to stop the session here and just remind you, as always, get lots of practice. Integration does require a lot of practice, so that's always the best way of revising.